Why does every careful experiment to measure the speed of light keep giving exactly the same number, c? In the energy filament theory, that stubborn c is a self-consistent ratio between lights, rulers and clocks that are all built from the same energy c, while the true relay limit of light in that c can still drift slowly as the universe evolves. On paper, measuring light speed sounds simple. You choose a path and call its length 1 unit. You use a clock to mark how long light takes to run that path, and you divide distance by time to get a number. It feels as if you are probing something outside yourself, a fundamental property of reality you can write down in a book and carry anywhere. In this picture there is a hidden assumption: the path, the clock and the lights are not independent objects. They are all patterns of motion in the same underlying medium. The universe is a stretched energy c. When that c tightens a bit everywhere, the maximum rate at which it can relay any pattern, including light, increases. At the same time, the atoms and molecules that make up your rigid rulers adjust their preferred spacing, so the meter marked on your stick quietly rescales. The electronic and atomic rhythms that define your clock also retune, because the swirling patterns that set their natural beats depend on the same background tension. Then you repeat the old procedure. You send light along a path defined by a ruler that has quietly shrunk or stretched with the c. You time it with a clock whose tick rate has quietly shifted with the same c. When you divide those two, the change cancels. The true relay limit may have moved, but your measuring system moved with it. So the ratio distance over time stays c. It sounds abstract, so try a more down-to-earth picture. Imagine a world made only of water. You are a person made of water, holding a ruler made of water and a clock built from swirling water, now slowly thickening the whole ocean, so water molecules can shove their neighbors faster. The real speed at which a disturbance can run through the ocean increases. However, the spacing between lumps in your water ruler also changes, and the timing of the swirls in your water clock shifts in steps. When you measure how many ruler lengths per clock tick, ripple travels, the numbers you got can stay exactly the same. Even though the raw molecular speed has changed, you've only measured a dimensionless proportion between 3 water patterns, not compared them to some external, rigid yardstick. That is what c really is in this view. A tight relationship between how light relays motion and how matter in the same c defines space and time. So why do we dare to say that particle properties evolved, but rarely talk about light speed evolving? The difference is in how many independent metronomes we compare. When we test c, we almost always use the same trio over and over again: light, plus a ruler, plus a clock, all cut from the same local c. We then go one step further and define our entire unit system so that c is built in by design. After that, verifying c mostly means checking that we have used our own definition consistently, which it does beautifully. When we study particles, we unintentionally do something more subtle. We compare many different rhythms whose dependence on the c's tension is not identical. We look at electron spectral lines, different kinds of atomic clocks, nuclear reaction rates, molecular fingerprints from distant galaxies, and the relative abundances of light elements like helium and lithium. Each of these listens to the energy c in a slightly different way. When we use today's particles and clocks to read signals that were written billions of years ago, those cross comparisons no longer line up perfectly. The mismatches act like fossils of an earlier c, hinting that some internal properties have drifted. That is how particles are changing becomes a testable statement, while true light speed is changing remains hard to isolate. In practice, we have almost never given c a truly independent opponent to fight. We bake it into our units, then applaud when it comes out constant. The energy filament theory does not dispute a single local light speed experiment. It adds one sentence on top. Those experiments show that within a given patch of the energy c, using rulers and clocks made from that same patch, the measured c is extraordinarily self-consistent. They do not prove that the deep relay limit of that c has been identical in all eras and all corners of the cosmos. To probe that deeper question, we have to read time fingerprints written into the sky. such as the uncanny smoothness of the cosmic microwave background and the horizon not enough time to talk puzzles that standard constant C struggles with. In this picture, if the early energy C was much tighter, its true relay limit for light and other motions could have been far higher, giving disturbances enough time to even out temperatures without invoking a special burst of inflation. Relativity remains safe, because it only insists that any local inertial observer, using their own rulers and clocks, always measures light speed as c, and we have not touched that rule at all. What changes is our willingness to let the underlying c evolve beneath those local measurements. In the next episode, we'll zoom in on what happens to your own time when you ride close to that local relay limit, and why pushing toward light speed makes your private seconds stretch while the c keeps its beat. Tap follow, share it on New Physics, Clear Universe.